Yeah, so the idea of successful collision is that whenever particles collide, they're going to do that with obviously certain level of energy. And that level of energy is required for a reaction to actually occur. It's not that every collision will produce a reaction. So they need to have, first of all, the reactants must collide. So I gave you the example of hydrogen and oxygen, that if hydrogen is colliding with oxygen, then only that collision is going to be useful. If oxygen starts colliding with itself or a hydrogen starts colliding with another hydrogen molecule, that will not be very useful for us, because for a successful collision, it should be between the reactants, between hydrogen and oxygen. Only then it can make water. Secondly, this collision must have enough energy. In A levels, you will talk about the angles at which they collide, but for now, we just need to know that they must collide with enough energy, which should be obviously at least activation energy. So, activation energy is the energy required to start a reaction. We talked about it in the previous chapter as well, the one on energetics. So, they must have enough energy for them to collide, and with that one, they will actually produce a reaction. So, not every collision will produce a reaction. It's only when they collide with enough activation energy that they're able to produce something. And that is why this is called fruitful collision in our local syntax. Like only in Pakistan, it's called fruitful collision. But otherwise, in your book or else, you will see that this is basically the idea is successful collision, that any collision that produces the required result, that is the one that we call successful. So we are going to solve a few questions on this today. And the main idea of collision theory is that if you can somehow increase the number of successful collisions, that if you increase how many particles collide with enough energy, then you can actually have a faster reaction. So the speed of reaction is just about having a higher collision rate. So again, the idea of time is important, that in how much time are they colliding. So let me give you an example. So I have a picture here to illustrate that. So for example, if you look over here, these are, so look at the first row. You have chlorine and hydrogen. And these are basically, so this is chlorine, this is hydrogen. These molecules are approaching each other. This line shows that they are bonded to each other. So hydrogen is bonded to hydrogen and chlorine is bonded to chlorine. So now they're going to approach each other and they're going to collide. But in this case, when they collide, they don't have enough energy. So what happens? They just go back. There is absolutely no reaction because they don't have the energy required to do this. But now, same molecules, if they come closer together and they do have the energy required, so this is supposed to show that they have the required energy. So when they collide, what's going to happen is that now you can see that bonds have been made. So one HCl and another HCl molecule is made. Earlier on, you had the reactants coming to go closer together with no energy or less energy. They just went away as they were. But now they have actually done a reaction. They have changed chemically. So this hydrogen might have joined to chlorine, and that is also joined to chlorine. And this is an example of how a successful collision is happening. Okay. Now, if I relate this to the uh, energy profile diagram that we talked about in the previous chapter, so let me just relate that. So over here, what's happening? So this diagram shows us how the particles collide. So these are the reactants. They're going to come close to each other. They're going to collide, and they need this much energy. This green arrow, it shows the activation energy, the minimum energy they need to start this reaction. And then they collide and they produce the product. And there's the delta H, the enthalpy change. So if you're hazy about this or you don't understand the graph, you can ask me now, or you can just go back to the previous recording. Okay, so what's happening in the first row? So these are the reactants, and they're coming close to each other, but their energy level is lower than this one. So probably they don't have enough energy as shown by this green arrow. They have a lesser level of energy. And what happens is that in that case, even if they collide, they will not be able to produce this. They will not be able to go into this transition state which they need before a reaction can produce. So if they don't have that, if they don't have this enough energy, they're not going to be able to produce any product, and they will obviously, this must be a non-successful or unsuccessful collision. Okay, so now what causes a collision to be successful, or where do they get their energy from? They always get it from the kinetic energy. That kinetic energy can be taken in from the surroundings. So for example, if you are doing this experiment and you heat it up, then these particles are going to interact with each other and they are going to have higher kinetic energy, which means that collision will be successful. Okay, so the more energy the particles have, the more successful collisions you are likely to get. And that means that if I have higher temperature, then that means particles will have more kinetic energy. When they have more kinetic energy, there's a higher chance that they will collide with enough energy to produce a product. So there's a higher chance that I will have successful collision. But how does that relate to time? So if they're moving faster, that means there's more collision happening per unit time, which means the reaction is faster. So for a reaction to be faster or slower, the idea of per unit time is very, very important. So we do this by measuring the time taken to get any particular product. Obviously, in the lab, we don't have it. But what do? We compare it to the product that we get. So we talked about different ways in which we can measure it. We talked about that we can take the mass if it changes, or the volume of gas, or pH, or temperature, and we are able to do that with respect to time, and we get, okay, we have this, in how much time has this much changed. So I gave you the example of this time and the volume of a gas being collected. So in the same interval of time, initially we have this much gas made, and then we have this much gas made, and then we have this much gas made. And if I plot it, I will get a graph, and that graph tells me pretty neatly how the gradient is changing, which means how many collisions are happening per unit time and how much product is made per unit time. And that way I'm able to see that, all right, when it becomes a horizontal line, reaction is not happening anymore. And that means my reaction is complete. Now, in the lab, we do multiple setups to do this. So for example, I'm going to show you a few of them before I talk about collision theory in detail. So for example, this is a setup. And I've taken this diagram from a book. So over here, you can see that what's happening is that you have HCl and you have calcium carbonate, and when they collide with each other, so they have added the calcium carbonate in it. Now, before they did that, the mass was 120.6. And after they added, the mass is 120.1. Now, this might seem a little counterintuitive. You might be like, mass doesn't change. So, what happened here? So, the thing is that when these things react, they produce carbon dioxide. And that carbon dioxide is able to go out of uh, this thing. So, this calcium carbonate, when it produces carbon dioxide, that carbon dioxide just goes out into the atmosphere. And what that means is that now you don't have that much mass. So how much mass has lost? You can calculate this by saying, all right, I had 120.6 and now I'm left with 120.1. So if I subtract them, that means I have 0.5 grams carbon dioxide that actually was lost to the environment. So if you took the stopwatch while this reaction was happening, so let's suppose this took 10 seconds for it to be produced. So your rate is going to be 0.5 grams made divided by 10. So that is 0.05 grams per second. Obviously, in O levels, we don't do these calculations. We don't have to, but this does give us a basic idea of how this is going to produce or how much gas is going to be made. Okay. You can also have some graph made in a way that you have mass over here, which is in grams. And notice that I put the mass, then slash and G. This shows that this is the quantity and this is the unit. And this starts at 120.6, goes down to 120.1. And this will always give us a graph that is a curve. We seldom get a graph that's a straight line. We usually don't get that. And the reason again comes down to collision theory. Why is the rate faster in the beginning? So in the beginning, you have more particles of HCl, you have more particles of calcium carbonate. So they collide with each other. So what do you get? You have calcium carbonate, you have HCl, and these particles are colliding with each other, and they're producing water, they're producing carbon dioxide, which goes away, and they're producing calcium chloride. Now, after a while, you start using up the calcium carbonate that you had. So less and less of this is available or left over because it has been used up. So now you will have fewer particles of these two things because most of it has already been converted to these things. So that means you have less of these. So initially you had so many of them which were all close together, but after a while they all transferred to the right side or they made the thing on the right side. So you have less and less of them available anymore. And what that means is that you will now have fewer collisions. Okay. So as the reaction progresses, more product is made, you have less reactant available. But simple here, you're using it up. So if you use it up, then you will not have it more of it left over. Simple si baat hai, it has been used up. And when it has been used up, the collision obviously is not going to be there, which means that as the reaction happens, we say that as the reaction progresses, you have less and less collisions available. Okay. So let me show you a simulation of this to show how this actually happens. That every time you get the idea of a reaction being faster or slower, it all comes back to collisions. That if a reaction is faster, it has more collisions per unit time, and if the reaction is slower, it has less collisions per unit time. And that is all that matters in any collision. And if you want to speed up a reaction, what you have to focus on is that if the question says, okay, how would you speed this reaction up? So the question you should actually think of is, how can I increase the number of collisions per unit time? And there are 5 factors that do that. I will see if the simulation has some of them, but I will also illustrate that in a while when we read about it. So here's the thing. So yeah, so this is a basic reaction. This double arrow means that this is a reversible reaction. So this is going to show me the energy. This is going to show me how far these particles are. And for now, I'm just using one particle to show how this happens. So I'm taking this particle and notice the green bar on the right side. If you notice that, you will see that if I increase it, it goes up and it shows that I'm giving it more energy as it goes. Now, for a reaction to occur, I need it to be happening at this level because that is when it has enough activation energy and it's able to collide and produce the product. But let me just give it a nudge, a very low amount of energy. So notice what happens when these particles collide with each other. You will see that nothing happens, right? So they come close to each other, they collide, but nothing really happens because it doesn't have the required energy. Now, let me reset this. Okay, now I'm going to give it more energy and I'm going to do that at an angle. So I'm going to do that at this angle, give it enough energy, which is just enough. Okay, so a little more than that. Yeah, let me do that. So it has activation energy, but it will not produce a reaction until it collides with that energy and at the right angle. So what happened here? I gave it enough energy, but it didn't react. The reason is that it slowed down over time, which means that it wasn't able to collide with the same temperature. So what do I do? If I want to give it more energy, I can just raise the temperature up. So now I'm raising the temperature. So as that happens, they're going to collide after a while. Hopefully, let's just hope that it happens. Now you can see that if I give them more and more temperature and they're just speeding up, they have higher kinetic energy, right? And what happened? So if you let me just pause this. So what has happened here? The reaction has occurred. So they collided with each other. And now, because they had enough energy, which was so much higher than activation energy, even though at activation energy they would have reacted. Now, what has happened is that they have the required energy and they have collided and produced a new thing. Let me try it one last time. Okay, so I'm going to do it now and I'm going to give it enough energy that it collides just enough. And there you go. And there you go. Do you notice that the bond, this thing over here, it shows that it has made the reaction. if you notice this, you will see that the reaction has occurred because they had the energy that was just above the activation level. So for particles to actually do a reaction, I need them to have a certain level of energy, activation energy, and without that, they will not be able to do this reaction. Okay. So this link, I'm going to share this with you, and you can go over here, change the temperature and all sorts of things, and you will see how many particles are able to react. Now, obviously, you can do the rate of reaction using the stopwatch here. So let me try this. Let's say initial temperature is just above the activation energy. I have this same reaction. I start with 10 of these, and I start with 10 of these as well. So I would expect them to collide, and I will see a graph. This graph will tell me how the reaction is occurring. Okay. So how many particles I have at a certain amount of time. So yeah, I think pie chart would be a good choice. Okay, so let's start. So I have these particles. Now notice, I have this division here. If I were to make a bar chart, and what happens is that I have A and these things, these two, they are our reactants, and these are our products. Okay. So what happens is that when A and BC, which is two different things, they collide with each other, they will produce AB and C, which is our product. So A and BC is our reactant, and AB and C is our product. So what happens here is that A should collide with BC with enough energy so that it produces AB, and that way the reaction occurs. Initially, I had 10 of AB, 10 of A and 10 of BC, but when the reaction occurred and I had enough energy, they collided. They've already produced two of this and two of that. Let me start the reaction, start the time, and see how long it takes for five of these to be made. So I'm going to stop the stopwatch when five of these have been made. Okay. So if they will collide, they will produce this, but you can see over here that temperature is low. That means they are not colliding as much. They're still doing it. Obviously, successful collisions will produce two of them, and you can see that now it has produced three, four, and it will take a while. And there you go. So I have produced six of AB. So it took me 453 milliseconds, or milliseconds, I guess. Yeah, that much time to do it. And that shows that I have done an experiment. I have completed an experiment. What's the experiment going to be about? I was calculating how long it took me to do it for six molecules. So that is 453. So on the side, I will make a table, and in that table, I will write that all right, to make six, I needed 453. I'll do the same. Okay. For making seven, it took 482. So I'm going to put it all on a table. So let's make a table. Over here, we have time in seconds or milliseconds or whatever the unit is. And over here, we have number of AB molecules. So I think for six, it took us 453. For seven, it took us 482. And yeah, let's see how long it takes to make eight. So it goes back because it's a reversible reaction, it's going back. I can also change it, alter it over here, or I can add more molecules. So because it's a reaction which is reversible, it will not produce eight in a while. It will take really long, and we will study reversible reactions in a while. Like it's the next chapter. So reversible reactions keep on happening, and as you can see over here, that's not reaching eight, which is what we want. But we can obviously push it to do that. I can produce more of these, and that way, it will produce eight of those eventually. You will see that it produces eight of them. I wanted to go to eight, but it's not doing it. So what do? I can do a few things, like I can raise the temperature. If I raise the temperature, I have given it enough energy to do the reaction, and now I'm more likely to get eight of those. Again, I will have to wait to see कि वो होता है कि नहीं होता या कितना time होता है. And there you go. It has suddenly jumped to 9. And at 9, I can see कि अच्छा 1848 seconds बाद उसने 9 produce कर दिए. And obviously, we made a few changes. Now I can draw this, I can put this over here that this is zero time, and this is time on this side and number of particles. So 6, 7, 9. So after 453, it's doing that. After 482, it's doing that. And after a long time, 1848, it's producing 9. And that means I can just use this to make this graph. Obviously, I haven't reached a straight line because the reaction was continuously happening. If it had completed, I would be able to get a straight line. But this is showing how the rate is changing. Now you can see, just to produce two particles, I had to wait a really long time. And this is telling me that because I had fewer collisions, the reaction was taking longer. So you can play with this and do different experiments of your own, change these things. So I would suggest that you play with this for at least once. Okay, so it will be quite useful to get a better understanding. All right. So how does this all relate to collision theory? So there are five factors in collision theory, factors that we can change, that we can control for a reaction to be faster or slower. So we can do that. And what those five factors are: one, you just saw that I increased the temperature. When I increased the temperature, they started moving faster. And when they started moving faster, they collided more per unit time. So the reaction was faster. For gases, we also have another factor, which is pressure, that you can give them more force, and when they have higher force of collision, they produce more successful collisions per unit time. So the reaction is faster. Why does this only work for gases? Because gases are the only ones in which particles are free. If you had liquids or solids, particles wouldn't be as free. Similarly, concentration is for particles that are dissolved in a solution usually. So how many particles you have in a particular beaker or in a small volume. And that way, if there are more particles, they are more rushed. So that means there's a higher rate of collision or a higher number of collisions per unit time. Then you have catalyst. What catalyst does is that it reduces the required energy. So it doesn't do anything to the particle, it just reduces the nature of the reaction. So now they are able to collide even if they don't have enough energy as before. So now the reaction will still produce more successful collisions per unit time. And the last one is surface area. If you have solids, you can keep on breaking the solid into smaller and smaller pieces. So if you have smaller pieces, then particles have more surface area. Let me show you how that works. So for example, over here, if you notice in the top left corner, then you have one big box, one big particle. And this has small surface area because it just has six sides. And anything that wants to react with it must collide on those six sides. But if I cut it in half, then I have six sides of one of them and six sides of the other. So I actually have 12 sides, and the surface area has increased because I have two new surfaces that are made. Similarly, if I slice it like that, I have four smaller particles, and things can now collide with these four particles on all the six sides of each four particles. So instead of having six over here, in just two slices, I have 24 sides where things can collide. Similarly, if I slice that or that or that, so you can see the smaller particle I make, the higher the number of sides and higher the overall surface area. Okay, so if you have a powder, then that powder will be reacting much faster than if you had some granules or larger marbles or larger particle size, because it has lower surface area. So it's inverse. Bigger the particle, higher the surface area. Okay, sorry, lower the surface area, and smaller the particles, higher the overall surface area. It's so overall surface area that matters. It's not the individual particle surface area that I'm talking about. So these are the five factors that affect the rate of reaction. Okay, and which that means that now they're going to affect the number of successful collisions per unit time. So that's another important thing whenever you talk about this. If you're talking about number of successful collisions, then you can put it in two ways. Either you can say that the rate of collisions has increased. What that means is that you have more collisions per unit time. So the idea of rate is related to time. The second way of saying that is to explain this. You can say the number of collisions per unit time is more. So you have to consider time as a factor whenever you're answering these questions. If you just say that there are more collisions, then that does not mean that the reaction is faster. Maybe there were more collisions in one whole year compared to 1 second. But the idea of time is important, that we need the same time for a comparison to be meaningful. So I want 10 collisions per second compared to 20 collisions per second, and that gives me a better idea of which one is faster. But if I say 10 collisions per second and 10 collisions per month, then that shows that one reaction is slower because I've changed the time or the unit of time. So that is important whenever you talk about collisions. Always connect it to how long it takes to do that. Okay. And that is the concept in this chapter. I'm going to share the worksheet with you in a bit. So, a few questions that you must answer for any, if you really understand this. So, another important thing, the idea of yield is how much product is made. So if you have higher rate, you will get higher yield. Okay. But in reversible reactions it will change a bit, so we will talk about those when we go on to reversible reactions. So that's our next chapter. So for today I'm going to share some MCQs with you, so make sure that you do that, and obviously some questions from past papers. uh, I will try to share the mark scheme with you as well. So if there's any confusion, we can always go back to those and discuss this. Okay. So yeah, that's it for today.